given the colloquium by our own Professor Douglas Finkbeiner, sitting over there, who spoke about artificial intelligence, a very exciting frontier, and it was sort of a talk after which you had a good feeling that we humans are still superior in some respects, given all the faults. But I bet you that in 100 years we won't be anymore, right?
Or 10 years.
Because it's exponential, right? The development of artificial intelligence is exponential.
Thinking that.
At any event, we will start today with Romane Le Gal at the CFA. She will speak about sulfur chemistry in planet-forming disks. And then we hear from David Barnes from MIT, not very far away. He will talk about radiative AGN feedback and dust formation with Arepo-RT. So that means the ending of this title means that it's theoretical. And then we'll hear from Doug again, and he will speak about Milky Way dust in 3 dimensions using star colors and the Gaia DR2. So that will be very interesting. And finally, we'll hear from Zhong-Zhi Xianyu. He is a postdoc fellow at the Harvard Physics Department, and he will talk about aspects of compact binaries in triple systems. Romane.
Yeah, so hi everyone. So first I would like to thank the organizer for providing me this nice opportunity to present a part of my work today. So I've been working in the field of astrochemistry for almost 8 years now, and during the last 1 year and a half I've been focusing on the chemistry of planet-forming disks, and in particular on the chemistry of sulfur that is occurring in those disks in the group of Karin Oberg here at the CFA, and this is what I'm going to present to you today. So planet-forming disks are disks found around young stars, and they are pivotal stage in the evolution from interstellar molecular cloud to planetary system, and in particular because they provide both the mass and chemical reservoir for the forming planets. And with the new generation of high sensitivity telescope, we are now able to zoom into those disks and to study in detail their chemistry. And so one of the main questions we would like to understand is how does their chemical composition and structures influence the future composition of the planets that are forming within those disks. And up to today, about 20 different species have been detected in such disks, which constitute only 10% of the 200 molecules that have been detected in space. But what is interesting is that 4 of these 20 species contain sulfur. And sulfur molecules are also found in the remnants of our own planet-forming disk, so for instance in comets in the solar system. And so studying the sulfur chemistry at the earlier stage of planet-forming disk can help us to understand the origin of the chemistry of our own solar system. So this constitutes by its own a very strong motivation to study the sulfur chemistry in planet-forming disks. And as of today, the disk sulfur chemistry is still veiled, so which means that, for instance, we still don't know what are the main reservoirs of sulfur in disk and what is the distribution of the main sulfur carriers throughout those disks. So in order to study the sulfur chemistry in disk, you first need to constrain the chemical network that is driving the chemistry. So here I have depicted such a network that we published last year for the study of prestellar environment, where a dozen of species of sulfur species have been detected. So here represented by the blue ellipses, and each arrow on this network represents a chemical reaction between 2 species. And each reaction needs to be determined either experimentally or theoretically. So here I'm kind of playing with the word simplified, because I'm not showing you here the full network that I'm including in my models, but I still wanted to show you a consequent part of it to show you that it's complete. It can be complex enough. And so when you have built and constrained this kind of network, you will implement it in an astrochemical model. And so here I will describe briefly how it works. So you need different inputs. So the key one is a chemical network, such as the one I just presented you. But you also need to constrain the physical structure of the source that you are willing to model. So that is to say the temperature of this source, the density, the visual extension, the cosmic ionization rate, the UV flux, and depending on the complexity of the source you are willing to model, it can be multidimensional. But you also need some information about the dust that you are implementing in your model, such as the temperature of the dust, but also the characterizing radius of the grain of the dust, which will influence a lot the chemistry that you are going to model. You also need some information about the molecules, so the physical properties of the molecules, so how do they bind into the dust, for instance, and also some information about the chemical composition of the elements that constitute your chemical network. So when you have all these different inputs, the code will compute the chemical abundances of each species that are contained in your network as function of time, up to a time that you set, and usually you will take a typical time that is the age of the source that you are willing to study. So for the purpose of disk study, so we want to build first the physical structure of disks. So here is a simplified schematic view of a disk seen edge-on, which is irradiated mainly by the central star, and which can be divided in 3 main layers. So there will be a top layer dominated by photons mainly, a subsequent layer called generally warm molecular layer, and from where most of the molecules that we have observed today in disk are supposed to come from, and then a deeper layer, the cold midplane, where most of the species are supposed to be frozen into dust. And we consider that these simplistic structures are symmetric with respect to the midplane. So for the purpose of disk chemistry modeling, we only consider half of this structure, and we compute the profile of the main physical parameters that are going to impact your chemistry. So that is to say the temperature, the density, the visual extension, the UV flux. So here represented as function of radius versus 8 in the disk. And this is a typical structure that I'm building and implementing in my model. And from this structure, you can then run the chemistry and compute, for instance, the abundance of the species you are interested in. So here, for instance, I'm showing CS, which is the most abundant sulfur species for the moment detected in disk. But you can do that for all the species that constitute your network. So here I'm representing a selection of 9 different species that are relevant for sulfur disk chemistry to show you how different the distribution of the species can be from one to another. So you see that they are peaking in different layers, but maybe interestingly, you can also see that some of the species present interesting ring structure. But for the remaining of the talk, I'm going specifically to focus on these 2 top molecules, so CS and H2CS, because we had some observation with ALMA that we can compare our model to. So with ALMA, we were able to observe CS in 6 different disks. So here I'm representing the emission from the continuum in this disk, and the second row represents the emission from CS in those disks, where you can see how extended is the CS emission in this disk. And if you look at the radial intensity profile of this disk, of this emission, you can see even some structure appearing in the CS profile. So here, this little bump is characterizing a ring. But you can also see, for instance, for some of them, that the CS emission is much more extended than the continuum. And for some of those disks, we even had multiple rotational transition for CS, which allows us to derive a specific temperature of emission and the column density of the molecule in each disk. And we can compare this value directly to our model results. So here I'm plotting as function of radius the column density and basically the temperature for the models that are represented here by the solid line, and the rectangle represents the observation. So you see that for CS, our model is not too bad in reproducing the observation, and can, for instance, help in better constraint from which area in the disk the CS is emitting. So we had similar results for H2CS. So we had 3 different rotational transitions that we found, but only in one disk. So we did a similar work, so derived a specific temperature, the column density that we compare to the model. But here we see that the model is not as good as for CS because we underpredict the abundance of H2CS. So it we might have some missing chemical pathway in the model. So this will need further investigation. But to summarize, with the new high spectral and spatial resolution that we have access to with the new facilities, we can now scrutinize the chemical composition and structure of planet-forming disk. And for that, astrochemical models are required in order to interpret those observations, but also to provide some prediction on the chemistry in this object. And we are currently waiting for further observation of sulfur species in disks, because we got an ALMA proposal accepted last year to further investigate the sulfur molecules that we already have with higher resolution, but also to have the detection of new species. So we are still waiting on that. And this will allow us to have a better constraint and comprehension of the sulfur chemistry in disk, and maybe also allow us to predict some abundances that can be expected and incorporated on the planets that are forming in those disks. And on that note, I would like to thank you for your attention.
So, Romane, there is this standard practice of comparing the data to models and getting agreement, but is there any data point that seems to be an anomaly that doesn't agree and indicates something completely unexpected with respect to the chemistry?
So yeah, I mean, for instance, if you look at, so here I'm comparing, for instance, the column density of H2CS that we compare to the model, and so with the model that we have, we couldn't reproduce the H2CS abundances, for instance. I mean the column density. So it means that, so it can mean a lot of different things, of course, but what we maybe think is that there are maybe missing pathways in our chemical network that could explain the formation of H2CS in the disk we're observing. But because the models are dependent on a lot of different parameters, so mainly the chemical network, but also the physical structure that you implement, so there are a lot of different bias that you can play.
You didn't mention ICEs. OCS has a very prominent ICE feature, among other wavelengths, at 4.9 microns that has been seen. So I'm wondering how much you think could be sequestered in ICE form that might be affecting these results.
Yeah, so in our model, so in the model that I'm doing here, I'm considering ICEs also. So there is already some species locked into the ice. And so here I'm only showing the gas phase species, the gas phase abundances. So there are already some sulfur locked into the ice, but that's true that maybe because the ice chemical network is less constrained than the gas phase one, because we still need to have more inputs from the experimentalist and theoretician on that side. And so we think that indeed for the ice chemistry, the network is probably still to improve, because maybe we are missing some reservoir in the ice, and because we cannot observe them for the moment. Maybe GWST will help us, but for the moment, since we only see, I think, OCS, and there was some tentative detection also for SO2, but it is still only 4% maximum of the total sulfur cosmic abundances. So there are still a lot of sulfur missing out there, and we don't know in which form and where it is.
In the very simple network of chemical reactions that you showed,
Yes.
you don't have to put on.
That's because we spent a little bit of time to make this, so yeah, I'm happy to show
Do
you.
you know the rate coefficients as a function of all the relevant parameters for each of those interactions?
Yes, so this is why I wanted to show how complex it can be, because you need to have some constraint on each rate for each of the reactions, and this is computed by chemists that we ask them if this reaction could be possible and if they could provide a temperature rate coefficient. And these depend on a lot of different parameters, the density, the temperature. So there are some reactions that are occurring in specific ranges of temperature, but not in others. So yes, we need to have a lot of different constraints here. So.
Why is some of them blue and some of them purple?
The blue are I didn't explain that. So, but the blue one are the reaction occurring on acid, and the green one are the recombination with electrons, and the other one are regular bimolecular reactions. So it was in order to distinguish those, but I didn't put the level here. So good question. Thank you.
Let's think Romane.
Okay, thank you to the organisers for the invite. I'm basically going to talk about some recent work that we put out in the archive at the end of last year. And this work is essentially done with current and former members of the ITC. And so we're going to look at radiative AGN feedback and the importance of dust formation to that within Arepo-RT. So I'm going to very briefly go through some observations of high velocity outflows, how we then implement AGN feedback within Arepo-RT and what Arepo-RT actually is. Then I'm going to go into what is really the meat of the paper, which is the importance of dust modeling. And then I'm going to finish with a quick glimpse of the future, because fundamentally this is really a sort of intermediate step to where we really want to be. So high velocity outflows. So when we look out into the universe at galaxies, and then we look at the black holes within these galaxies, there's a very strong link between the sort of mass of your black hole and properties of the galaxy. And so this suggests that there's essentially coevolution going on between them. But recently, there's an increasing number of observations of high velocity outflows coming from galaxies. And this is interpreted as sort of direct evidence of AGN feedback going on in action. And when you look at these on a plot, so this is from Fiore 2 years ago, it's just a compilation of all these outflows high velocity outflows that have been seen. So you can see over quite a large range of AGN luminosities, there's quite a large range of kinetic energies on the y-axis, but there's a reasonable correlation between these. And not only that, but these outflows exist in different phases simultaneously. So you can see molecular gas, ionized gas, see X-rays, and you can also see broad emission lines in these outflows. And the kinetic luminosity of the outflow is roughly, a few percent of the bolometric luminosity of the AGN. And when you really go into detail and looking at these broader absorption lines, you see there's actually sort of, a range of widths here, and these sort of go up to extreme outflow velocities of even, 10,000 or more kilometers per second. And the hard line on the left-hand side here is just a selection effect. But theoretically, there's a serious issue here in that we don't know exactly how you couple this sort of luminosity coming off the AGN to the surrounding medium. And so one of the sort of potential mechanisms that we're exploring here is radiation pressure acting on dust grains within the gas. And radiation seems to be important. This was a paper that came out, I believe, this week, looking at basically broad absorption lines. And you can see the dotted lines here are what are called line locking features. And so this is basically where you have a series of molecular clouds that are in the outflow, and they end up, due to various processes, getting sort of entrained at the same velocity with each other. And this sort of suggests that radiation processes play an important role in the dynamics of your outflows. Even if they're not the sort of key driving feature, radiation is important and often neglected in numerical simulations. So I'm going to come to Arepo-RT now. So this was work done by Rao Kanan over the last sort of 18 months. And basically, it's a radiative transfer scheme within the moving mesh hydrodynamics code Arepo. And this allows us to incorporate radiation. And in this way, in this particular instance of the implementation, we're using the M1 closure method. So the radiation acts essentially like a fluid within the simulation. In the particular simulations we're going to show today, we include both UV and infrared radiation. we assume that the radiation couples to the gas via dust grains, and that the dust grains are hydrodynamically perfectly coupled to the gas. This is an assumption that we're working to fix. And we also ignore thermochemistry, photoheating, and photoionization, because for the particular halo that we're looking at here, which is a Milky Way-like halo, it's sort of, especially in our implementation, essentially none of these things are important. So our initial setup is just it's just a uniform, relaxed NFW halo here. A Milky Way-ish mass. We assume a dust-to-gas ratio currently of 1% in this particular instance. And basically what we do is just put a black hole at the very center, and we just let it emit radiation at a constant luminosity. And so then you get this. And so after a period of time here, which I believe is 50 megayears, the radiation couples to the dust, drives an outflow, and you can see that the material is swept out. We achieve, in this particular case, about 1,000 kilometers per second of an outflow, which is reasonable relative to the observations. And you can see that the UV radiation here, which is shown in the bottom right, is basically absorbed by the dust as you go away. And we allow this absorption of UV to be reprocessed into infrared radiation, which is what the top right is showing. And so this infrared radiation gets stuck behind this outflow here because of the dust in it and scatters multiple times. And the reason that we kept the numerical setup so simple in this particular case is there is actually an analytic solution for this. And so we compare to this to validate our output. And so on the left-hand side here, what I'm showing basically is the position of the shock as a function of the virial radius of the halo as a function of time. The solid line here is the analytic solution, and the sort of band is where the shock is. So the analytic solution assumes a thin shell, whereas in our numerical simulation, we get a width to our shell, which is why there's a band. And we show two different luminosities here, a 10 to the 47 and a 10 to the 46. And we get a reasonable agreement with the expected analytic solution when you only inject UV photons, although the analytic solution neglects the sort of ambient medium of the halo which you're expanding into. And so this actually starts to cause the shell to decelerate relative to the analytic solution here. And when you allow this UV radiation to reprocess into the IR, then you get the right-hand side. And so the dashed lines here are essentially the solid lines on this side. And you can see that when these IR photons scatter multiple times, you get a big momentum boost. And so this boosts your position of your shock relative to the virial radius of the halo at a fixed function of time. And again, we see good agreement with the analytic solution here. So what you can do is you can take this particular setup, and then you can go and look at observational quantities like the mass outflow rate. And so the gray line here is just the mass outflow rate for the analytic solution, which assumes that photons are going in isotropically. And you can see our predicted mass outflow rate on the top here is slightly high because of the width of the shock, and also because the shock started slightly further out, as you saw on the previous slide. And then as you sort of essentially collimate this radiation, then your mass outflow rate goes down, simply because you're essentially focusing your radiation on a smaller amount of mass. But this improves other quantities like the kinetic energy, and that gets marginally faster. However, when you compare to observations, so coming back to this Fiore paper again, now you see essentially a set of opening angles at two different luminosities, and you can see that maybe for the sort of very low kinetic energies for a given luminosity, there's some agreement, but we certainly don't get the scatter. Now this scatter might be slightly over-exaggerated, but we don't reproduce the scatter at all here. And this is basically because of our sort of very basic setup. So, for example, halos contain galaxies, which was missing from the previous step. So what we do is allow that halo to then cool. And so this, with star formation going on, and so it forms this sort of disk galaxy here. And so this is its face on and edge on. Stars are on the right, gases on the left. And essentially, as the stars evolve, they can eject metals. And some of these metals will be in the form of dust. So we also follow this. And so this is work done by a PhD student at MIT, Ryan McKinnon, and he has several papers on this. So we're basically using the first two papers for this work here. And dust grains grow by contact with metals within the gas phase metals. And then we also include dust destruction mechanisms as well through shocks and sputtering, and this will become important in a second. So the impact of forming a galaxy is basically that it increases the optical depth of your halo, which is the critical point that you have here. So the deeper the optical depth, the better that your photons can couple momentum to the surrounding gas, because it's perfectly hydrodynamically coupled to the dust. And so the blue line here is just the original NFW. The gray line underneath is the analytic solution again for that. You can see that by the formation of the galaxy, you get this purple dashed line. And so you can see the optical depth in the center increases just because contraction of the halo due to the formation of the galaxy. However, if you also model the formation of dust, then you get this pink line here. And you can see again that your optical depth increases further in the center of the galaxy when you're modeling this dust formation. And overall, the formation of the galaxy with dust gives you a 2 orders of magnitude increase in the optical depth of the halo. For the dust formation, though, we're not modeling anything in the CGM because this is an idealized separate simulation. So it's isolated from everything else. And so again, you can play this trick and go look at the observational constraints for this. And now there are no observational data on this part, I'm afraid, but we can look at the relative difference of a galaxy relative to the NFW halo. So the NFW halo, again, is the blue line. I want you to focus for this point on the pink and the purple lines here, pink and purple lines here. And you can see that if you form a galaxy, then you basically increase your mass outflow rate, and your kinetic energy also goes up by about an order of magnitude as well. And so you're in better agreement, able to reproduce these sort of higher kinetic ratios and momentum fluxes for these objects. And that the formation of dust doesn't actually do a huge amount because basically you only have dust in the very center. So once the outflow is driven through the disk, then you don't pick up any more dust. And so you're not seeing a big difference there. The critical point here, though, is what happens when you actually model the destruction of dust. So these two lines here ignore the destruction of dust. And so this solid line here includes the destruction of dust. And you can see that basically your mass outflow rate drops again, although it's higher initially relative to the analytic solution. And your kinetic energy drops significantly. And this is because your dust is destroyed. So these three lines here show what happens if you don't destroy the dust. And if you do destroy the dust, you lose something like 70% of your dust within the first 1.5 mega years, and by the end of your simulation, you've only got about 10% of your dust left. And so modeling the formation of dust is really important to this, which is why all of the sort of crude setup that we've used so far is a serious issue. And that's where this work is going. So on the left here is, again, another realization of the galaxy that we use. And we're using this sort of Spring or Hörnquist type approach where you model anything that's star forming as an effective equation of state. So none of your gas gets colder than about 10 to the 4 Kelvin. Whereas on the right here, we're running the same galaxy, but now we allow gas to cool below this 10 to the 4 limit. And we actually reproduce a multi-phase ISM here, where we have 10 to the 4 gas in pressure equilibrium with 10 Kelvin gas. And so what we're doing essentially is reproducing all of the results we saw before, but now modeling this in a better way, which will give you a better understanding of how dust survives in these sort of red nuggety clumps here, and how that affects the outflow properties as well. So I'll leave you with my conclusions.
So, David, in terms of outflows from AGNs, there are two other ingredients which you didn't mention. One is that many of them are driven by lines, resonant lines that people found evidence for. And that obviously could give you more cross-section per mass than dust can. And second, that people argue that clumps are important, that you have small cloudlets that are flying out and they produce the output. Can you comment on that and whether it makes a big difference?
Yes, so that's, as I tried to sort of give an impression at the end, that is the critical step here, is that we really need to start forming these really sort of nugget sort of cloud dumps. And this is what the multi-phase approach will give us. And this sort of, this work here represents a sort of halfway stage where we know everything's working and we can broadly reproduce, but what happens when we really model this properly? But even this work here is a step forward relative to a lot of the numerical simulations that have been done to this point.
In resonant lines, you can do?
Yeah, that's something we need to discuss because, that might not be as trivial as the what we've got planned.
Charles?
So I may have misunderstood something that you said, but do you think you have both dust destruction and dust growth in the same environments? I thought once you're in an environment where your drift velocity leads to destruction, you're basically done. You're destroying all the dust. Is that right?
Yes. So throughout the so once we turn the AGN on, I should say, we destroy all the dust very quickly, and that's it. It's gone. But what we're mainly doing is trying to include all these processes in a more self-consistent way than just assuming a constant dust fraction, which is being done at the moment. But I agree we can model the dust better, which is something that we're still working on. But once you grow the dust, once you form the galaxy, but once you turn the AGN on, everything's basically being destroyed.
Rosie?
In your dust in terms of time, there was anisotropy at different thetas, right, that shifted up. Can you tell us why it's happened? It's like a flattened but shifted up, right?
This one?
Yeah.
So this, the sort of peak, are you talking about here?
Yeah,
some of this is,
thetas, right?
So some of the sort of wiggles, essentially, in this line, some of the uncertainties, that's basically how you actually define the outflow. And so it's not trivial as to how exactly you do that or identify what's in the outflow. So a lot of this is material that's basically, you've got material that's being accelerated but also dropping out. The other thing that's contributing to this is that you have, where you drive the outflow, you then basically suck material in the plane of the galaxy, or the plane of the NW halo in this case. And so that also then means that you have sort of essentially blobs of gas that sort of reach the AGN sort of feedback zone and then get fired out again. So that's also contributing to these wobbles as well.
Okay, well, let's, one last
Okay, just again about the dust. So what is the most important destruction mechanism for the dust?
Sputtering.
Huh?
Thermal sputtering.
Okay, and the population is the same, or is it changing between as temperature and between the phases?
At the moment, everything here in dust, the dust at the moment is all just a scalar quantity. So it's just, we just have an amount that's sort of stored with the particular cell. Part of Ryan's work, his 2018 paper, is modeling this in a better way. And so we're moving to that model. But that again requires us to do a bit more work before we can run those simulations.
Okay, well, let's thank David again.
Oh, I'm next.
It's already on.
Okay, thanks. Okay. Whoever came to the talk earlier will understand we learned how to become one with the zebra. But I'm going to talk about astronomy this time. So I wanted to take this opportunity to give pointers to a few things that my group has been doing lately. I know you should never talk about more than one thing at an ITC lunch, but I'm going to break that rule. So, and that's partly because some of these things we've talked about before and we have updates. So the 3D dust map you might be familiar with. This is a project we've been working on for 5 years, largely done by Green and Schlafly, and more recently, Catherine Zucker and Josh Spiegel have been doing a lot in this direction. And the idea is that you take billions of stars, use their colors to try to infer a posterior density on the space of all possible star types, metallicities, distances, amount of dust in front of the star, and so on. And then you marginalize over everything except distance and reddening. And do that 1 billion times. And we did that before, it worked pretty well, but now we have Gaia DR2. And how much does that help? So these are the before and after images. Each one of these is for one star. So here are 16 of the billion stars. And this is distance modulus and amount of dust, AV and magnitudes. And you can see there are a lot of cases where it's bimodal, there are degeneracies, right? It's not a one-to-one mapping from star colors to distance and dust. But when you throw in a Gaia parallax, a lot of these tighten up. You know, like if you look at that one, it goes from being very uncertain and bimodal to rather certain. Some of them don't, you know, just depends. But Gaia helps quite a bit, and that allows us, this is a paper by Catherine Zucker et al., that allows us to take these catalogs of molecular cloud distances. So my former student Eddie Schlafly did one of these in 2014 and picked out a bunch of clouds that people might be interested in. And then you see distance modulus and distance in parsecs down here. You can kind of map these dots down to these dots. So Catherine redid all of this and more, but just to make a plot that shows how much Gaia matters, we did this. So you see, you know, it was qualitatively right before, but adding Gaia tightens things up, makes the error bars a lot smaller in most cases. And, you know, we're firmly on a trigonometric distance scale now. So these should not really move by more than about 5% in the future. I mean, we really know the distances of these clouds now. So that's nice. There are other improvements in the new work. I'm not talking about like we marginalize over the reddening law RV now and things like that, but I won't go into that. The image, the animation I started with is the so-called Baystar map that Greg Green and others have been pursuing. And so we've got an update of that coming out that also is now tied to the distance scale in the same way I just showed you, the Gaia distance scale. We've gone from parameterizing the dust volume density in 30 bins to 120 distance bins. They're about 4.2 million pixels. They're about a half a billion volume elements on the sky, constrained by about a billion stars. So that's pushing it. So regularization is important, right? This fit could flop all over the place. You need some kind of, something like a Gaussian process regularization. So I'm going to show you a rendering now that's similar to the one I started with, looking in the same direction. We're still going around the sun at 50 parsec orbit, but this is going to render it against, as absorption against a model of Milky Way starlight. So the dust looks kind of the color that it would look in a realistic image. And you see the dust get sharper and then blurrier again. So this is showing what happens if we turn that regularization I mentioned on and off. So basically our previous map looked more like that, and our new map looks like this. So it's really tightened up quite a bit. Sorry? Sorry, yeah, this is just imagining what the dust would look like if we orbited the sun 10 million times farther than we do, just to get the parallax shift. Yeah, there are many ways to do 3D visualizations. I kind of like this one. But the point is, regularization helps. You can make these 3D maps a lot sharper than we were. So that'll all be released soon. In my limited remaining time, I wanted to point to one other thing. This is slightly more technical, but I think it's important. This is Josh Spiegel, who's upstairs, and Stefan Portillo worked on this. And what we realized in the course of a different paper was that maximum likelihood estimators can be biased. I think that's well known. But when you do PSF photometry on an image, and you allow the PSF to recenter to find, the optimal position for the star, that actually introduces a bias, and it's something like a 1% bias for a 10 sigma point source, which doesn't sound too bad. It's worse for galaxies. It'll be more like 2.5% for a 10 sigma galaxy. And where does this come from? These are just equations saying it's proportional to 1 over the signal to noise squared. And you also have a bias in the uncertainty estimate that's half that, but I'm less worried about that. Why does this happen? Well, one kind of heuristic way to think about it is if I force photometry at a known position, at the correct position of the star, it can fluctuate high or it can fluctuate low. Those both happen with equal probability. You add them all together, you get a distribution that's correct. But if the position's unknown and I let it recenter, what typically happens is if the pixels near the center are biased high, then it'll be centered. If they're biased low, it'll wander to some other location and try to soak up some flux there. Right, so this is biased high, this is biased low, but not as low as it should be. Okay, so then your distribution ends up getting skewed relative to the correct distribution. There's another way to look at it. I can show, what is the flux bias as a function of how far off center the star is. And so it can be biased 5 or 10% high if it's near the center and 5 or 10% low if it's around the edge. But they're kind of more near the center. The red histogram here is stars from the center, and the blue one, stars around the edge. And you see those are quite shifted with respect to each other, and the mean is the gray, and it's shifted with respect to 0. So these are just many ways of saying the same thing. So Josh and Stefan worked out analytically what this should be. There's a first order and a second order, or maybe I should say leading order and next to leading order term. So the blue line's a pretty darn good approximation for what we derive numerically from many realizations of data. But this is not merely theoretical. It's actually present in real surveys. So there's this survey you might have heard of, the Sloan Digital Sky Survey, that observed what they call Stripe 82 many, many times, 50 or 100 times, depending on how you count. And this is just an example of one band here. So we have the difference in the magnitude between what's observed in one run, one exposure on that object, and a stack over many, many exposures, okay? So it's sort of one observation minus truth, almost. And focus on the blue here. There's kind of a blue and a yellow superposed on each other, and you want the blue, greenish blue part. And the red is our prediction of how the mean flux as a function of magnitude should bend. And it fits the data pretty well. And this works in U band, G, R, I, Z band, works in all bands, works for good scene, bad scene. You know, it doesn't always fit perfectly, but it's definitely onto something. And importantly, this bias does not average away. If you observe many times, so this is a single exposure, this is 10 exposures. Let me just blink that for you. Right, the bias you're seeing, the yellow and blue there, doesn't particularly change as we go to many exposures. The noise gets a lot smaller, so it becomes more significant. But this dashed line is what our model predicts. The solid line is what our model would naively predict if you used the signal to noise of the combined measurements. But it's the signal noise of the individual measurements that matters. And it's worse for galaxies. So a galaxy with a signal noise of 5 has about a 10% bias. So just to summarize that, there's this maximum likelihood bias. It scales as 1 over signal noise squared. It appears in SDSS at the level expected. It's worse for galaxies than for stars, and it does not average away. So if you're going to do a survey with many repeated measurements of lots of faint galaxies, you might think of one of those coming up. You should watch out for this. So I'll stop there.
So they improved the precision of your 3D map. Does it allow you to address questions like how does the dust to gas ratio vary in the galaxy, or like grain size distribution varies?
Oh, you want science? Yeah, that was just mapping. If you want science. So actually, Eddie Schlafly has done something very interesting with this, looking at the Redding law variation from place to place in 3 dimensions, which we can start to do now. And there's a correlation between that and the microwave emissivity function. Okay, and that correlation has not been understood really until recently, but my student Joanna Jelko has been working on that, and we think we have an explanation. So yeah, what's nice about having these 3D maps is you can start to dig into the actual properties of the dust. You can look at how it's reacting to the radiation field it's in. You can actually make 3D dust temperature maps. And sort of the big picture long-term plan here, which maybe I should have started with, is we'd like to have a map of everything. We'd like to understand the distribution of everything in the galaxy, the 6-dimensional radiation field, the cosmic ray propagation, the magnetic field, you know, all these things all fit together. And having a map of where the material in the ISM is really kind of the foundation on which you build all those other things. So if, for example, you want to understand the gamma rays that are in the way when you're looking for possible signals from dark matter annihilation, you want to understand all those other things I just mentioned.
By the way, this parallax that we see is at the edge of the Oort cloud, roughly, right? A million times the Earth.
Yeah, we're out at, actually this is 10 million AU, I think, 50 parsecs.
Oh, 50 parsecs.
Yeah. So it's way out, but it's fun. Things kind of look like they should. You've got the Orion stuff, and Mon R2 is twice as far away, and then there's the things further out in the plane. It looks just like it should. We have fly-throughs also, but I have limited time.
Other questions for that? Yes?
Okay, your photometric bias result, why, when you do repeated measurements, does the effect on average away? For your heuristic explanation, each time you do the measurement, isn't it the fluctuation away from the true position? Wouldn't it be in a random direction?
Well, but it's really an honest bias, right? So on average, you're wrong, and if you take many averages, your noise keeps going down as root n, but you're still wrong by the same amount.
Wrong in a different direction?
So are you thinking of this figure like positionally wrong in a different direction? Because you are, but you're still, the fact remains that the bias low when you're off center does not fully compensate for the bias high when you're on center. So if you average a bunch of these, it just... it doesn't change. Now you can do a deep stack, stack the images and then do the photometry on that, but that has a host of other problems. And so it could be the safest thing to do is find the sources in the deep stack, go and force photometry near them, realize you're making this mistake, and correct analytically for the mistake.
I was going to ask if
It's
your
a possibility.
analysis suggests a better way of doing your problem.
Yeah, another thing is I should emphasize that if you are a good Bayesian, you determine the entire posterior for position in flux, not just the maximum. If you have the entire posterior and you marginalize over it, you get the correct answer. Okay, this bias is only coming from the fact you're not marginalizing.
Is there a last question over there?
Well, I had a similar question, I guess, for the stacking procedure that you showed. So you're stacking the fits, not fitting the stack. Is that right?
Right. Exactly.
Okay, let's thank Dr.
Okay, so good afternoon, everyone, and thanks a lot for the organizer for inviting me. And today I'll talk about binary and couples. Today is particularly nice for talking about couples, and just to add a little bit more drama, I will talk about triples too. I was ignorant enough to put many papers here. I didn't know the practice here, but hopefully I can finish in time. So the work was done with Lisa Randall, also from Harvard Physics, and our works were motivated, of course, by the LIGO discovery of binary black holes. And I'm sure that all of you have seen this many, many times, but there remains a big question, that is, where do these binary black holes come from? It turns out that this is a very difficult question. It is difficult because gravitational waves are weak. So we cannot rely solely on gravitational waves to put two black holes together. So people are talking about different mechanisms to drive two black holes together. One is so-called common envelope evolution. So in this case, two black holes evolves in isolation. There's an alternative channel called dynamic formation where you can have something else. But today I'm going to focus on dynamical channel because this is the place where a third body can enter the play. And the question is, which one is correct? Okay, to talk about the dynamical channel, the third body, the general goal is that the third body will help the binary to merge rather than to break them up. So the third body had better to stay not too far away, not too close to the binary. So in this situation, we speak of a hierarchical triple. So this is a perfect example of hierarchical triple. This animation shows you why a third body can help the binary to merge. The idea is very simple. So this triangle is formed by the angular momentum of these two orbits. And you can see that some large inclination configuration can subsequently evolve to a configuration where the angular momentum of a small orbit can be very small. So small angular momentum means large eccentricity, which also means small periapsis distance. So in this case, two black holes can be very close to each other and effectively turn on the gravitational wave radiation. So this is why a third body can help. This is the so-called quasi-leader of oscillation. And here I'm just plotting you the semi-major axis in blue line and eccentricity in purple line as a function of time. And you can see that at some point, the eccentricity can indeed be very large. And at that point, the gravitational waves can be strong enough to reduce the orbital size. So this kind of picture provides us the first answer to the question of how to distinguish two different channels. We know that in dynamical channel, when there is a third body, typically you will have some large eccentricity. So the answer is that just to measure the eccentricity in LIGO. Of course, as series, you also want to predict what will be the eccentricity from the very beginning of the triple evolution. Of course, an obvious way to do this is just to do numerical simulation to evolve your triple system numerically until the two black holes be very close to each other. But just to save you some time, a bit of time, we propose an analytical mapping which can map the triple parameters directly into the eccentricity you see in LIGO. This works particularly good for small eccentricities. And I will not go into the detail of this formula, which is hopefully not too complicated, but just to show you some distribution of eccentricity in LIGO you would expect if the binary black holes in LIGO were from the galactic center, for example. And if you look into the labels here, you might say, okay, this answer does not work because this eccentricity is in log scale, and the LIGO is supposed to measure eccentricity as small as 0.01. So 0.01 is here. So LIGO is going to measure only the tail of this distribution and cannot quite distinguish different scenario of the black hole distribution. But fortunately, we have another instrument in the future, which is LISA. Since LISA will be measuring black hole at much lower frequency, at that stage, the eccentricity of binaries will be larger. So LISA will basically reveal the full distribution of the eccentricity and hopefully tell whether it is from dynamical channel. So this plot is just to show you that actually people did some work showing that the binary black holes observed in LIGO can actually show up in LISA too. And LISA actually can be more wonderful than just measuring eccentricity. So next I will provide another two answers to the question of how to distinguish the binary black hole. The second answer is that we can look for the very center motion of the binary. Since now we have a triple, so the binary will orbiting around the third body. This just works like a binary pulsar. So since we have a motion, we will have some Doppler shift, and Doppler shift will be in the gravitational waves. So you measure gravitational wave frequency as a function of time, you will reveal the orbital parameter of that large orbit. So just to highlight one point, so the period of this orbital motion is nothing but it's proportional to the mass that enclosed by the large orbit, but inversely proportional to the distance cubed to the center. And this is nothing but the density enclosed by the large orbit. So by measuring this period, you are actually measuring the density of the black hole binary environment. So this is indeed a very good way to tell whether you are in a dense environment or not. And just to put some numbers in to tell you why this can work. So typical case, a supermassive black hole in the center of galaxy, million solar mass, and 100 AU away, you have orbital period perfectly 1 year. So if you turn on LISA for 5 years, you will be able to observe 5 orbital motions. Of course, if you are very far away, then perhaps you will just resolve a small portion of the orbit. But even in this case, even you have a large degeneracy, you can still measure a non-zero acceleration, which will be a signature of something is there. And the last answer I will provide is that you can actually directly measure the Kozai-Lidov oscillations in the binary black hole. Why this is possible? It is because the peak frequency of gravitational wave radiation from the binary actually is controlled by the periapsis distance. So at early stage of Kozai oscillation, even you have very large semi-major axis, but your eccentricity can be large. So effectively, the periapsis distance can be so small that the peak frequency is just in the Lisa band, like 0.01 hertz. And the variation is so significant in here 6 years that you will see something drastically different from the standard chirping signature of the binary. So this will be another perfect way to see the difference. By the way, so the quasi-Lidov oscillation was proposed in 1960s, and nowadays we have very rare direct observation evidence for that. And this will be a perfect way to observe quasi-Lidov resonance. Okay, just to summarize, 2 take-home message. So first one, a third body can indeed help to merge rather than to break up. So not always bad. Second one is that Lisa can tell if there's a third body in several different ways, so stay tuned. Thank you.
From your presentation, imply that you cannot see anything in the gravitational wave signal itself because it's the third body is too far away, right? The tidal effect is negligible.
Oh, we are saying we will see the gravitational wave from the binary, not
right,
the.
But the tidal effect of the third body is negligible on the gravitational wave itself.
In LIGO, yes, because what LIGO see is this part. And in this part, the third body effect will be very small. Lisa will be able to see something here. So in the last slide here, Lisa will be able to see this resonance in early stage due to small periapsis distance. So in principle, you can resolve this kind of shape. Yes.
Roseanne?
This is really very interesting and beautiful.
Okay.
There's a kind of a complementary thing that Dan D'Orazio and I were working on, because there could be an electromagnetic signature if your third body is providing mass. So then you might have some mini disks around the black holes, which will eventually merge, and one black hole can lens the mini disk of the other black hole. So you would see some sort of spike in X-ray radiation, and that would actually, and this can best be seen, in the systems that would be detectable with Lisa. Best be seen if we do get the X-ray emission links. We can only do it very nearby for Chandra, but farther away for links. So we should talk about this because it's a very nice coming together of these different approaches.
Thank you. Welcome.
So why your eccentricity increase by time? Because eccentricity is always decreasing, right?
Yes.
In your profile.
You mean this one?
Yeah.
What's the question?
Early on, in terms of time, your eccentricity increase goes to the saturation and then decrease. Why it has an increasing profile?
Oh, why it is increasing?
Yeah.
This is a question. Because apart from the quasi oscillation, there will be periapsis precession due to the PN correction. That precession will somehow reduce the period of this quasi oscillation. So at some point, it cannot oscillate to very small value just due to this precession. So it will be increased to some point.
Is this only for triple systems or for any systems you expect to have that increasing pattern?
Good question. Only for triple system, because for pure for isolated binary, you will only have circularization like this.
Yeah.
Yeah.
So at any event, if we need to summarize your talk, Lisa has implications for your future career in 2 ways: your collaborator and the future instrument.
Exactly. Yeah.
That's thank you, Zhong-Zhi.